So when we left off last time, we had a solution to y equal to ax that took advantage of our singular value decomposition. V transpose with x hat was equal to V sigma inverse U transpose. So we actually have this is such a useful concept, and it shows up over and over, but we have a name for this. And this is the pseudo inverse of A, and we usually write it in this way: A dagger. For this first time, I may as well make a credible attempt at a dagger. Usually there's some typeface that does it well, something like that. In future, we'll just make a plus sign up there, or a lowercase sans serif t. That's equal to V sigma inverse U transpose. Okay, so you've probably run across way back in the distant past something that looked like this. A transpose. So this is the pseudo inverse for a full rank A with m greater than n. So there are various forms that you can use, but this near algebra in second grade or whenever it was, you have something like that. But this definition, the pseudo inverse in terms of the singular value decomposition, works for m greater than n, m less than n, non-full rank A. It works always. It always gives you something that will give you a decent solution to the problem y equals ax. So let's go a little deeper into this. One, let's see. There are a few interesting facts here. One is when y is in the span of u1 through um, we have beta naught is equal to u naught transpose times y. That's equal to 0. So r is equal to 0. In this case, we have there's at least one exact solution. And the one we choose is our x hat from above. A x hat is equal to y. Okay, and that's that highlighted x hat right up there. Next, if r is less than n, then the solution is not unique. So in this case, V naught has at least one column. And so what essentially is happening is any part of our vector x that is in this V naught space, subspace, can't be seen by A. And so we could then pick a solution in the span of V, the columns of V, and then we could add to it any linear combination from V naught to produce an infinite number of solutions. So let me write this. In any part of a vector x in the range V naught is not seen by A. Now what do we mean by that? Essentially, if we had A, V naught, alpha naught, so this is the part of x that is in the subspace spanned by V naught. It's just going to be U sigma V transpose V naught alpha naught, and this is always going to be 0, so that's equal to 0. Apologize for the noise there. There we go. So, as a result, we could define x hat is equal to, or x prime is equal to x hat plus V naught alpha naught. So, how do we do this? And that's for any alpha naught in R n minus R, we will have exactly the same residual. And why? It's because A x hat, or x prime, is just going to be equal to A x naught. So, what do we do here? Remember back a few slides, we said that when the unique solution exists, use that, and we'll do that. When no solution exists, return something reasonable. And so we came up with our x hat is equal to V sigma inverse U transpose times Y. That was reasonable. Why is it reasonable? Because it minimized the residual. And then the last thing we wanted to do was, when there are an infinite number of solutions that exist, we should choose the best one. Well, what's the best? Here we've got an infinite number of solutions, parameterized here by our x prime as a function of alpha. So let's just choose the one that has our smallest norm. Choose solution. So here we're not looking at the smallest residual, we're looking at the smallest norm of the solution vector itself. In other words, let's find the smallest x hat that would work. So I think we all kind of know what that's going to be, but let's just walk through this. We want to minimize this norm. So this represents all possible solutions via our choice of alpha naught. And so that's equal to x hat plus v naught alpha naught x hat plus v naught alpha naught, which is just x hat with x hat plus 2 x hat with v naught alpha naught plus v naught alpha naught with v naught alpha naught. And we already know that this is just x hat squared, and the last term is going to give us v naught alpha naught squared, and those are positive quantities. So the only thing we have left to worry about is this middle term, and we can write that as x hat, which is v sigma inverse U transpose Y with v naught alpha naught. Now when we perform that inner product, we take the second term, find the transpose or the Hermitian transpose, and multiply it by the first term. So we would have v naught transpose times v, and so those two things cause this goes to 0 because it contains v naught transpose v. Okay, thus we get the norm of x naught hat plus the norm of alpha naught. So what happened to the v naughts? Well, remember, this is going to be alpha naught transpose, v naught transpose, v naught alpha naught, and that's going to be an identity matrix, leaving us just with the norm squared of alpha naught. Okay, if we want to minimize the norm, then we have to choose alpha naught equals 0. So choose alpha naught equals 0 to minimize the norm of x hat. Well, if that's the case, Then we're right back to where we started, which is that, excuse me, we have x hat is equal to v sigma inverse u transpose times y. Remember, this is a dagger as our solution. And the nice thing about this solution was it minimized the residual, and it also minimizes the norm of the solution itself. So we have the smallest value of x that actually solves this system. So let me just about out of room. I just want to put this here. Two things. One is in MATLAB, x equals a backslash y is the same thing. And two, this minimizes r and x hat. So that's using the SVD for least square solution. We'll talk about next time the reconstruction error associated with that.